Title will come up soon. Semi-infinite q-boson systems with boundary interaction.
Okay, of course I'm very grateful to the organizers to have the opportunity to speak here, but I'm even more thankful for the great service to the community that they did to organize this workshop here in such a nice place. And well, to do my part of the bargain, I will talk today about q-boson systems. And in particular, I'm interested in q-boson systems on semi-infinite lattice. So, yeah. Since not everybody might be completely very well versed into these systems, let me give a brief overview of some of the literature. I think the q-boson system was probably first discovered by Bolo, Bogolyubov, and, well, Pang. There are maybe other papers which are a bit older, but in the version that I will talk about today, it's in this paper probably. So what is it? It's a system of quantum particles which is managed by creation and annihilation operators which satisfy a Q oscillator algebra. And the particles can move on a ring, so a circular lattice, or on just the whole integer lattice. The first really detailed treatment of this paper of this system was in the second paper by Bogolyubov and Izergin and Kitanine, and they proved that this system is integrable using the quantum inverse scattering theory. And they also derived the eigenfunctions in the spectrum using the algebraic beta ansatz. They studied the system on the finite periodic lattice. Then there was a paper by Zilewicz, and in that paper it's shown that the eigenfunctions that of this system are actually very well known functions, namely Hell-Littlewood functions. And that's where I got interested in this system, because, well, Hell-Littlewood functions play a big role in my own research. And, well, very recently, a paper of Christian Korf appeared in the CMP, and there, well, everything was cleared up in some sense. It turns out this is not just any model, but it's really at the heart of a lot of algebraic combinatorial theory of symmetric functions, and then not ordinary symmetric functions, but symmetric functions where you trade the permutation group for an affine permutation group. And one particular thing that was interesting for me, that was proven in that paper, is that, it's a long paper, there are many things proven, but one thing that's interesting for me and also for this talk is that it was shown that in the n particle sector of the q-boson model, that is equivalent to a discretization of the delta potential model that I had introduced a few years before, and which was the topic of the talk of Erdal Emsis also. Well, so those first four references mainly talk about the system on a periodic finite lattice, and what I'm talking about today will be the system not on a finite lattice, but a semi-infinite lattice. So it means that we have a boundary, and we can put boundary conditions, hopefully integrable, and that's what I want to talk about today. So, to define the model, yeah, it's a particle model. I said I talked about creation operators, annihilation operators. So I need to define a Fock space. So the Fock space is built of particle subspaces, and the n-particle subspace is just the space of functions over the integral lattice. But since we're dealing with like bosons, so we can divide out by permutation symmetry. So that means that we can restrict to a fundamental domain of Zn modulo the permutations. And we're also interested, in our case, since we have half infinite lattice, in functions which are even in the coordinates. So, well, the bottom line is that for n-particle Fock space will be the space of functions over the partitions of length at most n. Yeah, so divided out by the permutation symmetry and the evenness in the coordinates. And for n equal to, it's those that lattice of blue dots. So that will be the n-particle subspace. And now, to define the model, I have to introduce the annihilation and creation operators. Well, here they are, but it's better just to skip immediately. I actually don't know which button to press, so better not. I did it right. It's best to skip right away to the bottom of the page to the notation. So I've introduced some operators on partitions. The beta k star, what this does with a partition, it adds one component with value k to lambda. And where it does, well, it depends, it respects the ordering, of course. And beta k lambda deletes a component with value k from lambda. Well, supposing that there is such a component, but I will only need that definition in case there is. And mk lambda counts the multiplicity of components of the partition with value k. So those things I need. And I need a direct delta, which is supported in the origin also. Other things that pop up, yeah, we're dealing with Q oscillators, not ordinary oscillators. So we need Q numbers. They're in red down there. So this is the Q deformation of an integer. If Q is 1, it's just the ordinary integer. And if Q is 0, it's always 1. And well, notice also that the number 0 and the number 1 doesn't get deformed at all. Is a talk button? Yeah, no, I found it, but anyway, I'm not sure. I always point in the right direction, but thanks. So, well, having these notations, here are the creation and annihilation operators. So the annihilation operator should map the function of n variables to one less, and it goes by this duality that you see in the first. Oh, yeah, that's what I mean. You see in the first line, and the creation operator does something similar, but the other way around, and it multiplies also with Q numbers. The red one is the Q number, and the blue one we can ignore for the moment. Think of C equal to 0. It's a boundary effect. So if C is 0, or if you're not in the boundary site, K equal to 0, then that factor is not there. It's only there at the boundary. And this Q to the nk here, it's like the number operator, but the number operator itself is not in the algebra, so it's the Q power of that. It counts the number of particles as a power of Q. Fine. Well, so this is the definition. These things satisfy commutation relations. The important ones are above in red. So the red ones are the commutation relations of the Q oscillator algebra, and the blue ones is a perturbation at the boundary. So these are the commutation relations at the site K, and if you have operators from different sites, then they commute. So it's ultra-local. Yeah, here some other notation. This is like the Q number of the number operator, or what did I, yeah. So it's easy to check this from the definition, but it's not so interesting for ourselves. But here you can see that these are really, is really a representation of the Q oscillator algebra. Well, deformed at the boundary with this constant C. If C is 0, then it's just the ordinary Q oscillator algebra. Okay, well, this is not really how people normally introduce q-bosons, so I'll provide a link to what people normally do. If we consider the characteristic function which supported on lambda, and I write it down with this cat here. So the usual interpretation of such a state is a configuration of n particles where you have nk lambda particles at site k. So k runs through the whole non-negative integer lattice, and the number of particles is nk lambda. In total you have n, the length of the partition number of particles. And what do these operators beta k star and beta k do? Well, they really act as annihilation operators. Here they add a component, they add a particle with at the site k, and here this one adds and this one deletes a particle at site k. And this one counts the number of particles at site k. So here is an example. I've written down the partition, and so in the standard interpretation this corresponds to particles distributed over the integers. And since you have one component 1, there's one particle 1, and etc. The creation operator adds a component at 2 with value 2, so it means adding a particle at the second site. And yeah, you see here, it doesn't matter where I put a 2 here, you always get the same partition, of course. And, oh, sorry, this is not correct. And here this one deletes. So this is how one normally thinks about these q-bosons. But for me, I think about these q-bosons just as some operators in this Fock space, and well, will not think much about this interpretation. Okay, so here's the Hamiltonian. We have the Fock space, we have the creation and annihilation operators. So now, to have a dynamics, I need a Hamiltonian. And it's just a standard quadratic Hamiltonian. And the blue part moves the particle to the left, and the red term moves the particle to the right. And you have at the boundary also this diagonal term proportional to the number operator. And this has to do with the boundary condition. Part of the boundary condition comes from here, and part comes from the deformation of the algebra at the boundary. So what does this Hamiltonian do? Well, in the bulk it just moves particles from left to right, and at the boundary it wants to move to the left, but there is no side there, so it reflects with a certain phase. And that will be the boundary condition. Okay, so we have Fock space, we have the creation and annihilation operators, and we have the Hamiltonian, and now we want to find the eigenfunctions. It's clear that this Hamiltonian preserves the number of particles because you have equal number of creation and annihilation operators. And so what we first do is compute the action of this operator in the n particle subspace. And here is the answer. So if you have a function in the n particle subspace, so on this on the space of functions on partitions of length n, then this is how the operator acts. So you see here this term comes from the diagonal, and here you get like a difference operator, and this difference operator is very much like a Laplacian. If all those coefficients would be 1, then it would be just a discrete Laplacian, because you're summing over all the neighbors. You sum the function over all the neighbors in the lattice. So here I've drawn, where is it? Here I've drawn in dimension 2 the lattice, so it acts as a Laplacian by summing over the neighboring points. If you're at the boundary here, then of course there are only 2 neighboring points, and here you also here are 3 neighboring points. So if all coefficients would be 1, it would be just an ordinary Laplacian, and so the only difference is now that the coefficients are not just 1, they are like these q numbers here. And you have also this factor, which is appears only at the boundary when lambda j is equal to 0. So that corresponds here to this boundary. Now, generically, in the bulk, this coefficient will actually be 1, because then the multiplicities will all be 1. If you have a partition in the interior, then all the parts will be different. So these numbers all will be 1. It's only at the boundary where the coefficients are non-trivial. So that leads to think that you can solve this eigenvalue problem for this operator with the beta ansatz, because you have a discrete Laplacian, which is just an ordinary Laplacian in the interior with boundary conditions. And indeed you can, and here's the answer. So here's the beta ansatz wave function. It's a linear combination of plane waves. And now, what are the coefficients that make this an eigenfunction? Here they are. So here you see the boundary parameters. This is one from the diagonal interaction, and this is the one from the deformation of the q-boson algebra. And here is the q of the q-boson algebra. This is the way how these parameters enter in the expansion coefficients. I will come to that. I will come to that. I mean, it depends. If I see this operator, I know enough. But so I'll tell you how it works. This is actually a very well-known function. It's like a generalized Hell-Littlewood polynomial, but it's polynomial in the spectral parameter. This psi here is the spectral parameter. And as a function of psi, it's a polynomial. You have these denominators, but because of the symmetry, these singularities actually cancel, and it's a trigonometric polynomial. And this case in particular is known as the Macdonald spherical function for the root system BC. So this function is very well known. And so why is it an eigenfunction? Well, so the proposition is that this is an eigenfunction with this eigenvalue. And if you look concretely what that means, it means that this function should satisfy this relation. This is just the action of the n particle operator on that function. And so this is the eigenvalue equation. The fact this proposition translates to this identity. And this is actually an identity for the Macdonald spherical function that you can squeeze out of the literature. If you look at this as an identity for these trigonometric polynomials, this is like a recursion relation, because you multiply the trigonometric polynomial with an elementary trigonometric polynomial and expand. And this is a recursion relation that's called Peary formula. And the Peary formula for the Macdonald spherical function you can squeeze out of the literature. There are Peary formulas for Macdonald polynomials. This is a special case, and you can see that this formula holds. So it's easy to check that it's an eigenfunction if you know enough about symmetric functions. How to prove it from scratch is much harder. And the real ingredient here is that you use the Peary formula, but that's a very non-trivial formula. So this identity is very non-trivial, and it's not easy to prove, maybe at this level. You can prove it using affine Hecke algebras, but that's not easy. But I know this formula is true, and I know where to look, and so I just use it. See? Okay, but now.
Sorry, what was the CJ that appeared in
Yeah, this is the spectral parameter. So it's a C is a vector with component C1 to Cn. It's the spectral parameter. Here's the eigenvalue expressed in terms of the spectral parameter. And it is in this variable, the spectral variable, that everything is polynomial. So not in the discrete variable. Okay, so we've advanced a lot. We have the eigenfunctions. And we know that they are Macdonald spherical functions. Well, Macdonald wrote down a lot of properties of those functions. One of the things is that these are orthogonal. So they are trigonometric polynomials, and they satisfy this orthogonality relation, where the integration measure is in terms of the C function. And you have to integrate over the torus, but since you have this permutation symmetry and evenness, you can actually restrict to this fundamental domain. And McDonald also computed the normalization formulas for that. It's built out of q factorials. Here they are. And shifted q factorials. So this you can just squeeze out of the literature too, if you look well enough. Of course, the formulas are not given in this way, but this is the way that's convenient for me. Okay, so this means that if we have an orthogonal basis, it means that we can associate with that Fourier transform. And this Fourier transform will diagonalize the Hamiltonian. So here I've defined the Fourier transform, it's inverse. And now I pass to the convention that I put all the normalization constants inside the wave function, right? So, and the integration measure also inside the wave function to work really with self-adjoint operators with respect to a uniform measure. So it means I apply a gauge transformation towards my n particle Hamiltonian. And then summarizing everything, we get the following theorem, namely that the n particle Hamiltonian is unitary equivalent to the following multiplication operator, just the multiplication by the eigenvalue.
You have orthogonality, but don't you need completeness as well?
That's trivial, because you're dealing with polynomials. It's trivially complete. Yeah, it's just Stone Weierstrass. So that's trivial. So the Hamiltonian is unitarily equivalent to this multiplication operator. So now I have to apologize to the audience and the organizers. The spectrum will be continuous, so it's not discrete. So, of course, I didn't put that in my abstract, otherwise I would be out immediately. And we can also even compute really the spectrum. It's just this band from -2n to 2n, and just the range of this sum of cosines. But for me it's good news that this spectrum is continuous, because it means that I can do scattering theory. I have a system, not with bound state, but I have scattering behavior. And so that's what I want to discuss at the end now. So there is a natural reference dynamics, namely if you put all the parameters that we had, the boundary parameters, the q, if we put them all equal to 0, then the coefficients of my Laplacian will all be 1. And I just get a discrete Laplacian on this lattice with coefficients 1 and with like a Dirichlet type boundary condition, in the sense that the neighboring points outside of my grid, they don't count. Okay, so that's a very simple Laplacian, and the eigenfunctions are very simple. Instead of these McDonald spherical functions, in that case you just have like the corresponding Schur polynomials. They're called wild characters, because the root system, we are dealing with not with a symmetric group, but with the BC type hyperoctahedral group. But anyway, that's just details. The point is that this is a very simple Laplacian. The eigenfunctions are very simple, and actually this model has also been studied. Well, maybe not on so much on the half line. Or on the half lattice, on the semi-infinite lattice, but on the infinite lattice and on the periodic lattice, and it's called the hard phase model. So this will be the reference dynamics. So here I've written down the q-boson dynamics. Since we have diagonalized the system, we can just write down the action of the dynamics in terms of an oscillatory integral of a wave packet. So here it is. And now I'm interested in the dynamics for large times. And the idea is that for large times, we are away from the boundary, so the coefficients of my q-boson Hamiltonian are equal to 1, so they coincide with the for large times with these. So the idea is that we can compare the q-boson dynamics, which is in principle more complicated, with this simple dynamics. Well, as any physicist knows, well, I'm not a physicist, but they tell me. If you want to compare the dynamics, you have to calculate a scattering matrix, and to do that, you just look at the asymptotics of the wave function. But we have a beta ansatz model. That means the asymptotics of the wave function is the wave function itself. So remember that I put all these measures and so on in the wave function, and if we expand that in terms of plane waves, then we get these coefficients. Here they're a product of bulk factors and boundary factors, and these are the two-particle bulk S matrices and the boundary S matrices. Here are the explicit expressions. As I've put in also the square roots. It's not because I think you don't know how to take a square root, but just to fix the branch. So this is how I take the square root. And yeah, so here is the bulk S matrix. Yeah, you have differences and you have sums because we are working on the half lattice, the semi-infinite lattice. Well, this was informal, but you can make this completely rigorous, and then you get the following results. So with time-dependent scattering theory, you can demonstrate that these operator limits exist, where H0 is so the reference dynamics, and H is the q-boson dynamics. This limit exists in a strong sense, and you can compute it. So these are the Muller wave operators which you compute here explicitly in terms of the Fourier transforms. Here F0 is the Fourier transform with the corresponding to with the Schur polynomials, and this is with the McDonald spherical function polynomials. And so this is the Muller wave operator, and then by combining them you get the scattering operator completely in a rigorous way. And the way to make this rigorous is using a stationary phase analysis, using the plane wave expansion of diagonal functions. So this formal computation here, reading of the S matrix, is made rigorous here. Well, those are the results. Let me end up with some supplementary references. So I used a lot of spherical function stuff that you can find here. If you look at the right place, the necessary formulas are here, and then you have to take some limits and things, and you get them. Then I used some scattering theory too. Actually, the scattering theory of such discrete Laplacians was studied in a much more general setting by Rauschenhaus, who looked at the case of Laplacians corresponding to particles on the full lattice, and I adapted it a little bit to also include particles on the semi-infinite lattice. Actually, this paper is completely written in terms of abstractly of a root system and things like that, but the necessary results for proving this are drawn from there. So, thank you. The Q goes to 1 limit. It's analytically very poorly behaved. So it's you see this already if you look at the ordinary Schrödinger operator with delta potentials, right? Then you have the infinite coupling constant limit and the zero coupling constant limit, and simply. The infinite coupling constant limit is much better behaved than the zero coupling constant limit.
But algebraically, your modified q-boson algebra with the boundary interaction, that should still be well defined in the q goes to 1 limit.
Yes, but one thing that changes that all your creation operators and annihilation operators, because you have this q regularization, they are all bounded operators, and for q to 1, they become almost like ordinary creation operators and annihilation operators for harmonic oscillators, and they're unbounded. So analytically, it's a very bad limit. Whereas if you go to q equal to 0 at the level of algebra, that's a bad limit maybe, but at the level of the Hamiltonian, it's a very good limit. So I simply don't know how to make all this stick. For the q equal to 1 limit, but
I mean, physically, I would think that this is just the free. I mean, that should be the free dynamics. I mean, from physical things, because then you really get free bosons. So if you just would look at the bulk, the q-boson algebra, and the q goes to 1 and becomes the free boson, the normal free boson thing. So then you would think that is the free reference dynamics.
Yeah,
Right,
but if you try to make it stick, then well, at least I don't know to prove all this stuff.
Yeah.
We see it's apparently it behaves much better if you compare with this q equal to 0. Yeah.
Further question? Oh, that's thank you.